introduction. Very helpful. Yeah, what I'll discuss today is about deep seabed mining, and myself, I'm more from the engineering sciences, but I try to provide a more broad perspective, so also including some aspects of legislation. Clearly, environmental impacts is something to discuss, and yeah, I'll take it from there. Um, yeah, first of all, we notice as a society that we are facing an energy transition, and we move away from fossil fuels with the desire to move towards renewable energy. And in order to do that, we need a lot of materials. And there's especially what you see for instance, in the energy transition for the automobile industry or for power generation, we see that the metal consumption significantly increases for, say, compared to fossil fuels. So for power generation, we see that we need a lot more, clearly a lot more copper, but also nickel, cobalt. They are quite interesting materials there. And also what we see is that with the increase in need that society would need, there are choices to be made in terms of where we get the material from. We can think about recycling, and that's definitely something we should do. But there's a challenge there. You can only recycle things that are at the end of their lifetime, and you cannot do that from the start. But definitely, it's something to consider. But at the same time, we also have to be aware that to meet the demand, that eventually mining is necessary. And where we do mining, uh, that's up for discussion, and that's something that we need to figure out what are the places where we can collect the primary raw materials with, say, the least impact, so that they're best for society, and that would contain environmental, but also societal impact. So that's something to be considered. Now, then, yeah, as I will talk about deep seabed mining, and the main question here is deep sea mining a viable option? And first I'll discuss this based on a few aspects. I'll zoom in a bit on, say, what kind of deposits are available and why are they interesting, and what are, say, typical challenges to do that or associated with those. What are exploitation technology concepts? What do we have to think about? How to do it? What are the main challenges there? I'll focus a bit on the impact assessment and monitoring of environmental impact. I'll consider some of the legal aspects and also try to highlight, say, the main things of the way forward. I have to apologize. I could easily talk about this for, say, full day, but I have to stick to 20 minutes. So it will be a bit high level, but we'll get there. So for the marine deposits, for deep seabed mining, there are typically three types of deposits that are considered to be of high interest. Those are hydrothermal vents that are volcano-like areas that are typically close to the edges of, or close to the ridges of the tectonic plates. And these are rich in copper, zinc, gold, silver, and cobalt. And they are typically at water depths beyond 1 kilometer water depth. Now, then we have another category, and that's the one that gains most attention also in the public domain. Those are polymetallic nodules, and they are, like here shown at the side, they are potato-sized and shaped objects, basically rocks that are very high in, or especially in interest of copper, nickel, cobalt, and titanium. Mostly the business case is based on copper and nickel. And they are found at the abyssal plains of the oceans, and they are spread like here on the right, just like on top of the seabed, only really the top layer, with abundances of typically 10 to 20 kilograms per square meter. And then we have finally ferromanganese crusts. Those are, say, similar kind of deposits like the polymetallic nodules, but they are now, instead of in nodules, they are more shaped like a crust on a rock substrate. and they're typically found near sea mounts or on sea mounts. As you can see, all the water depths are quite deep, so ranging typically beyond 1 kilometer, and the deepest or the most interesting, the nodules, typically at 4 to 6 kilometers. And that is also one of the main challenges for technology, because offshore oil and gas hardly did not go beyond or hardly went beyond 3 kilometers. And if we look at the amount of material that's available, we know that there is really a lot of material available at those places that might provide us access to additional resources that we otherwise wouldn't have based on land. So that's why we consider, or at least why we investigate whether deep sea mining can be an option. Now, if we look at the locations, yeah, so in the most interesting area for polymetallic nodules, that's here in the Clarion-Clipperton zone. So that is the area between Hawaii and Mexico, and that is where most of the licenses are. Exploration licenses are granted for doing exploration, whether you could consider exploiting that area. So what we know, what's currently the status at this point in time, it's only possible to get an exploration license. So you have the freedom, you have the obligation to do exploration under such a license, but also you have the freedom to develop and test your equipment, and you have the obligation to do an environmental impact assessment. And you also need the equipment to actually do that the kind of impact, because how you would exploit or what kind of technology you would use definitely determines what kind of impact is to be expected. The rules and regulations for exploitation licenses, they're currently still under development, and those rules and regulations, they have to be adopted by consensus by all 167 member states that are member of the International Seabed Authority. I'll come back to that in a few slides. But what's part of the challenge here? So if we look at the maritime zones, based on how far you get offshore from the coast, how much authority or how much ownership you have as a nation or as a coastal region changes. So 12 nautical miles we have the territorial sea, so there we have full sovereignty. So the nation has the full rights to everything that happens there. Then up to 200 nautical miles offshore, we have the exclusive economic zone, and that is where you have sovereign rights over the natural resources of the water column and the seabed and subsoil. Nations can extend for the extended continental shelf. If you get that granted, then you have up to 350 nautical miles. You have sovereign rights of the natural resources of the seabed and the subsoil, so typically minerals and oil and gas. And beyond that area, it is what we call the high seas, and that is basically owned by the globe, by the global community. And that's why it's being governed by the International Seabed Authority. And this is where most of the interest is for deep seabed mining in that area. And it's organized, or the authority has the mandate to organize and control all activities in the area. And they have the responsibility to develop mining regulations, but also to do it without serious environmental harm. And that definition of serious environmental harm, that's something that is still up for discussion, how that should be interpreted. That's between the stakeholders, there's quite some different interpretations there. But that's part of the negotiations to draft the regulations. But the ISA, it got installed in 1994 as part of UNCLOS. And UNCLOS is the United Nations on the Convention on the Law of the Sea, and that is a treaty that how we should handle the area beyond the national jurisdiction, so the high seas. Its headquarters is in Kingston, Jamaica. There are currently 167 member states, so not all nations have ratified the UNCLOS. And EU is a member state, or at least is attending there as well. There are also 99 observers, so of which are 30 states, 32 international organizations, and 37 NGOs. So it's a huge or quite a strong diversity of interests that is being presented there. And out of some might also ask, there are only 167 member states. That's less than all the countries. That's true. One of the special or one of the countries of interest that is not a member state but an observer is, for instance, the United States. So yeah, that's but together. So with all those member states, they have to develop or approve regulations based on consensus. So that's where the whole challenge comes into play of getting the regulations in place. Currently, there are 31 exploration contracts, so 19 for polymetallic nodules, 7 for hydrothermal vents or seafoam-acid sulfides in that sense, and 5 for the ferromanganese crusts, so the CRC. If we look at what's happening, so in 2021, there was the first successful test with nodule collector vehicle in the deep sea by GSR, and that's the Belgian contractor, which was also monitored fully independently by European research community, fully funded by the European governments, so without funding from the company. So that's why you also see here 2 vessels. So the red vessel, that's the vessel that GSR used. The blue vessel is the vessel that the researchers used. Last year, there was another test that was done by Alsys and the Metals company, and that was where they collected, where they not only had the mining vehicle working, but they had the full system. So also getting the material, collecting the material at the seabed, bringing it to surface, dewatering, and getting rid of the excess of water back subsea again. And these kind of tests are essential to develop the input needed and to gather the data needed for the environmental impact statements. Because without testing this equipment, you will never know for sure what kind of impact you're likely to expect. Otherwise, it still remains, say, theory. So part of it is of these tests is also to prove whether it can be done. So that's and we see now that for those pilot tests that the research or that the data has been collected, still a lot of data processing is ongoing, and we see that the first results are getting disseminated. Now, why is deep sea mining a challenge? I'll first explain a bit about, say, the overall layout of the technology. So at the seabed, or at least we typically divide the deep seabed mining system in several subsystems. The first is at the seabed. We have a tool that needs to collect the ore, and for nodules, they are just to be picked up. But for the crust and for the hydrothermal vents, we really need to excavate and need to dig in and crush rock. But that's the seafloor mining tool. The collected material needs to be brought to surface, so we have a flexible host connection to typically a riser-based system. That brings the material from seabed to surface. It's a challenge because we're talking about several kilometers instead of just like in conventional operations of a few tens of meters. Then at the vessel, we need to store the ore and dewater it, so get rid of the water. The excess of water and sediment needs to be discharged back subsea, and because the operations are that remote, we also need to consider that once in a while, the ore that has been collected needs to be transshipped to bulk carriers to do the transport to shore. Now, part of the challenges for deep sea, first of all, we're talking about water depths of 1 to 6 kilometers. So thinking about an environmental pressure of 100 to 600 bar. And I think you all have seen the news a couple of months ago about the Titan Explorer. It's a very hostile environment in that sense. So it's a challenge to develop technology that can handle and operate in those conditions. It also means that we're in an area that's very remote. so there's no existing infrastructure available that we could depend on. So everything has to be operated from a vessel, and because of the depth, it also means that all operations need to be fully remote. We cannot send people down there. Now, if we look at what we have done at TU Delft, we've done a lot of research on the vertical hydraulic transport of the slurries, on the excavation processes and turbidity. And I'll show a few things of the excavation processes of the work that we've done and of turbidity. So we've done in a consortium in a European project called Blue Harvesting, where we developed a new type of collector system. So we make use of the Coanda effect, so that we create a high velocity jet here at the bottom, and that helps to entrain water, and at the same time it helps to suck up the nodules. So it acts a bit like a vacuum cleaner, aiming to minimize the disturbance of the bed. Now, what you see here at the top right in the video, we also made use of recirculation because we want to minimize how much sediment we're picking up, and we want to and we need to separate. We only want the nodules, and we don't want the sediment. So we try to get the sediment separated at the seabed already to leave it behind. I'll come back to in some of the next slides. And we want to change the condition in which we release that. So using less water means that we could increase the concentration of the sediment that we leave behind, and that's very convenient in terms of flocculation, and that's what I'll show in the next slides. We've also conducted some tests, so in experiments of what happens behind the vehicle, and in such a tank like this, it's called a lock exchange. We have a mixture compartment. We can create a mixture of water and sediment. We can release the lock, so we can release the gate, and then we get a turbidity current flowing, and that's typically what happens behind the vehicle, what we see. So the excess of sediment and water that we collect with the system, we try to leave at the seabed, and we want to study how that behaves and how we can actually influence that to minimize how much it disturbs the environment. And that's also where flocculation comes into play. So we know that in the area there's still quite a lot of organic content present, and organic content, so say poo of and remains of dead animals, is very helpful because it's sticky and it helps the sediments to start to stick together. And that's what we see here, that we get actually larger flocks. And those flocks, because the particles start to stick together, they tend to have a higher settling velocity, meaning that the plume settles by closer. And that's very convenient because that means that we would disturb a smaller footprint than we would do if this phenomenon would not be occurring. We also did it with a PSE. We studied how this effect works. So what we see here is a vehicle that is moving, and we see, say, the material that's being discharged behind the vehicle in terms of the concentration. And what we've learned is that flocculation is a process that's really can influences what happens behind the vehicle. So we see that, yeah, we initially start with clay particles that are very fine, but at the end of this domain, so after already say 70 to 100 meters, we see that those particles start to stick together, create larger particles, and that is very important for impact assessments because that means we get higher, larger particles and higher settling velocities, and thus effectively less sediment remains available for far field transport, and that is one of the environmental impacts. So by looking at the source that what we're dealing with, we can make better estimation of how much sediment would be available for transport, and thus how much the environmental impacts might be, or at least the environmental disturbance there. And if we look at the environmental impact, so I already mentioned the collector plume, but in deep sea mining there are quite a number of other impacts as well that get the attention. So just starting from the left, if you look at the seabed, it's the collector plume, so the sediment that we bring up into suspension that that might travel outside or beyond the mined area, And the reason that we're careful about that is because it's an environment that is not used to any turbidity, so any suspended sediment. And thus the local fauna might be quite sensitive to that because due to, for instance, that they need to filter the water to get their food. And if then sediment goes through the animals, that's not healthy. And also, for instance, it could also cause some blanketing. So if the sediment deposits, you get a new layer of sediment. But if animals need to filter and scavenge the seabed for food, and if it's buried, then you're blocking their access to food. Now, there's also light disturbance because we're in an area where no natural light can penetrate. So all the light that we use with our equipment might hinder the local species that make use of bioluminescence. Now, we're also in an environment where typically there's no human activity, and we work with our machinery, so we create noise. At the surface, we have to think about how we're powering the entire system. So typically, greenhouse gas emissions are important. We also have to think about toxicity of the material that we're dealing with, because it might be normally naturally contained in the seabed. But if we start mobilizing the seabed, it might not be, it might move to different places. So we have to think about it. And in that sense, we can do a lot about, and we can directly measure, say, the environmental pressure. So that's the turbidity. So that's the activity that we actually, or the change that we create. But the real thing that we are interested in is what is in the end the effective impact of the pressures that we apply. And that gives one of the main challenges that that's currently being faced, and that is for the draft regulations to also come up with, say, the threshold values that the operations should be held against, and measuring tolerance thresholds for environmental pressures in the deep sea is very challenging. We have to keep in mind we're talking about an area of several kilometers deep, meaning that any species that we would try to recover to surface basically won't survive the travel to surface because of the pressure difference. Meaning that we have to conduct measurements in situ, so at location, and that's extremely costly because we have to do that with robots. We have to have a research vessel there. We have to, for instance, use a box to enclose, for instance, a sea cucumber. We can expose them to certain toxicity or to certain substances in a controlled way. But then you can measure it for one animal, and that makes it quite complex to make robust analysis of how much. So say what doses is harmful. So that's something we have to think about. And also challenge there is we can only identify, say, the short-term impact, because that's only when we're there observing. We're not able to track the species, how they will do in a week time or in a month time. So that is something that is currently under development, to come up with advice of what thresholds should be put in place to make sure that the impact is deemed acceptable. And I think there's also a nice thing there that from the Dutch government managed to get one of the Dutch scientists involved in that work group to help out in defining what thresholds to think about. Now, also, as Renee already mentioned, deep sea mining is a topic that is getting quite an active debate. Very clearly, opposition and proposition are very active. And we have to navigate through that. One thing that we have to keep in mind is that any extractive industry has an impact. there's uncertainty about the impacts, and we as scientists try to unravel what is the impact that is likely to happen. We also have to keep in mind that doing nothing has an impact, and in principle, mining has a cost, but not mining also will have a cost. So in terms of, for instance, that we have to do it at other places, or that we have to accept that we get less materials. It's a choice. But at the current status, we're still awaiting the impact analysis of the pilot mining tests that they are to be finalized. We see that commercial interest is increasing due to the successful tests. So from technology point of view, there's confidence that it can work. We also see the increased intensity of the debate, and that's especially due to a clause in the UNCLOS that was initiated slightly more than 2 years ago, which means that in 2 years' time there should be regulations that the International Seabed Authority didn't make it, but now there's an agreement that by summer 25, then the regulations should be in place. So yeah, we're awaiting how that process gets along. And what we see in the discussion very often happening is that on one hand, there's an argument about climate and thus say the energy transition and providing the materials needed to adapt for the energy transition, and at the other hand, the challenge of say the local environment. So how to balance it, yeah, we'll have to see. That's in the end, that is a political decision. Part of the things that need to be developed and that are ongoing work is for especially effective legislation and management and control. So that's also the viewpoint of the Dutch government, is that the rules and regulations need to be clear, transparent, and need to be practical. So you need to be able to work with it, and everybody should be held against, say, the same standards in that sense. We need to make sure that we have the environmental thresholds, that they are defined, and that we can actually monitor on those and see in due time whether those thresholds are really fitting, or that we need to adapt them, whether they might have been too strict or that they might have been too loose. We'll have to find out. And at this point, the mining code for exploitation is not yet finalized. So that's something that needs to be finalized in 25. And then I would like to acknowledge some people. So I'm very happy that in the Netherlands we are able to have a very constructive debate among both proponents and opponents, and actually have good discussions rather than just widening the gap, but trying to figure out what are the things that we need to do it in a proper way. And I would also acknowledge some of the colleagues. So we work on this together with the Netherlands Institute for Sea Research, so NIOS, University of Utrecht, especially for international law and the law of the sea, and at TU Delft, especially the group of Offshore and Dredging Engineering. And that's about it. So if there are any questions, feel free to ask.
Thank you very much, Rudy. I think that was a very nice overview of both the technology, but also the kind of dilemmas that are related to deep sea mining. I can already see one hand raised. So Florian, please go ahead.
Hello, thanks for the nice introduction in the topic. I have a question. You mentioned also in the talk and also a lot during the talk, responsibility. And of course, responsibility always requires monitoring. And I'm kind of struggle with the scale of the operations and the scale of the monitoring approaches you presented so far. So like this in situ monitoring, as you said, quite costly, and also these are punct measurements for like one species then. So my question is basically, how can we control the thresholds are really kept? Thank you.
Okay, it's a very broad question. First, something to clarify there is that there's a difference between monitoring and environmental impact assessment. So monitoring is typically what we apply for say the direct operation, and that is something that has to be done during the operations. And what we expect that will happen is that, especially at the start of a project, the monitoring is required to be very intense. Also to confirm whether the impact assessments are to what extent they were correct, and also to enable the both the authority and the contractors to adapt. That's an important thing there at first. Another challenge that comes into play is that the monitoring should be done at least legally fully independent. It's a challenge because it's very costly, and yeah, you need to share resources. So most likely it would be that most of the monitoring will be conducted by the contractor, but it should be done in such a way that all the data that will be collected will be shared transparently with the authority, and also that it will be reported on that, so that say all relevant stakeholders can look into the data and also see what happens there. What also happens is, for the impact assessment, it's not only conducting the test, but it's to do the impact assessment, you first need to develop an extensive baseline. So gather data for at least 1 year full-time of the site that you're going to work at. You need to identify reference sites and also monitor those. Then during your operation or during your test, you need to monitor, say, the pressures that you're generating. And after the test, you need to make a couple of visits back again to the area to identify how things have changed over time. And you can do that immediately at the end of a test, but also a couple of months later and a couple of years later as well. And all that kind of data needs to be collected and needs to be shared. And what I notice, and I'm very happy about, is that the industry basically says that's all environmental data that they are willing to share. So that's, compared to other industries, something that's already not being done there. So that's a very good thing. Yeah, so I hope that answers a bit of your question.
Yeah, thanks. I have a question that's a bit related to that. I think
Yes.
if you look at these types of environmental risks, which are related to often the release of toxic compounds, there are two approaches. You can either have a risk-based approach, or you can have a precautionary principle-based approach. Normally, that's already an interesting discussion in terms of, let's say, there's something that within a reasonable time frame can also be restored, basically. I mean, if you're talking about emissions to land or to water, etc., at a certain moment, also mining. I mean, there are a lot of efforts to reclaim the land after the mining operation is finished. Now, in this particular case, we are looking at an ecosystem that will never restore, basically, right? I mean, if you're talking about the nodules, you take away the nodules, they take millions of years to actually develop. So these will never return in our lifetime or even far beyond that.
Yep.
So it will be destroyed in that respect, at least in terms of the nodules, will be destroyed forever. And then the question between the risk-based approach and the precautionary principle approach becomes more interesting, because then you say, well, if you know it can never be restored, then the risks are so high that you could argue, well, in that case, we would like to avoid actually doing that kind of damage, of which we know it will never be restored. So I'm really interested to hear your view on.
So here the question is actually, so you're changing the local environment permanently. That's for sure. You remove material that will not grow back on, will only grow back on geological timescales.
Right.
What typically is now being addressed, or how it's being approached, is what's the criteria that you should say, what kind of impact would be deemed acceptable, or say what would be the red line of impact of what was not acceptable. And most governments are on the line of that no loss of ecosystem functions are allowed. So that is the impact that needs to be shown.
Mm-hmm.
That's not going to happen.
Mm-hmm.
And within that constraint, mining would be an option.
Okay, because I could imagine that even with that criterion in mind, you could argue that there are quite. I'm not a biologist, an ocean biologist, but what I hear from those people is that some animals are and some ecosystems are really dependent on the nodules being there. So in that sense, that part of it at least will not be restored.
That's also no, but there's also an interesting thing there. That's a colleague at NIOS, Sabine Gollner, has placed a set of nodules in a test area to study whether it would be possible to help reseed the area, and whether say leaving or replacing nodules with artificial nodules would be an option. So they are, she made them from say remainder of the deep sea clay. So various kinds of materials and various different processes of how to manufacture them. They are installed, and she has a very nice thing. So every couple of years they go back to the area when they're in the vicinity with a research vessel, and they'll collect a few of those nodules and study what has happened. So also for her as a scientist, very nice, because she has at least an experiment running until her retirement.
Yeah.
But it is very valuable input to know whether it's going to be an option or not.
Yeah.
So unlike on land, there we say rehabilitation gives a bit more opportunities of how to consider and what we could do. Deep sea, it's more challenging, and but yeah, we need to study and we need to figure out, and that's part of the work.
Yeah, thanks. I think that's an interesting approach also. If you could reseed, let's say, with other nodules that basically have the same function. I mean, I think it's the physical form. I mean, the content of the nodule doesn't really matter, of course, for the ecosystem probably. So it's more like the physical form that matters.
And I think also a very important aspect here is, I think often the perception is that say a nodule field would be stripped entirely. There's also the question whether we should do that or not. So also part of the studies is to figure out, should we mine the entire area, or should we say create certain strips where we collect material but leave also some areas untouched? In terms of ecosystem connectivity and all these kind of aspects.
I've also seen systems where they basically not have this let's say vacuum cleaner cleaning but picking them up one by one basically, and then just doing the half of it or something like that.
That's it is. I'm aware of that system, and it's a very interesting system. But at this point, so from technical point of view, there's quite some challenge because it's not yet mature enough for these kind of operations. And just to give an idea of, say, the scale of economy that we have to think about, the smallest scale systems that have been studied is in the range of 300 tons per hour production, and that would mean that you would have to pick up about 1,000 nodules per second.
Yeah, that's a lot.
Yes, and then doing it by grabbers one by one, it is a logistic challenge.
I just see a swarm of robots picking them up.
But still 1,000 per second is a really logistic challenge.
You need 1,000 bots then. Maybe Bernard, you have a question.
Yeah, really interesting discussion. Thanks a lot, Rudy, for your talk. I was almost asking the same question that has just been asked, but I think we discussed it enough. My other question is about the sort of the effluents or the releases of substance back into the water, because I could imagine that there is a lot of fine grained material. I don't know what the ships do, if they do processing of the material already, or if that happens on land, right? But if they process, then even worse. Then there is
the only process that you would do offshore is only separation, so getting rid of the water. But further processing of the nodules you would do onshore. It's too power intensive to do that offshore. It's never possible to afford that. There is a debate about at what water depth the return water needs to be discharged. There's clarity on that. There's at least a minimum water depth. I'm not sure about the exact depth, but I thought at least below the minimum oxygen zone in the water column because of the potential chemical reactions. But then the question remains whether you should do it at, say, 1.5 kilometers or back to the seabed. The challenge there is...
And what do we expect in this effluent, or I don't know if we should call it tailing, not... yeah.
Typically, there's the sediment that has been collected and was not being able to separate at the seabed. So there's some sediment, and most likely fines from the nodules bumping into each other. So nodule debris, and that's most of the material base. And of course, it's water from deep sea that's being transported. So say the composition of the water at that place. As far as I'm aware, there's no other additives to be included. So it's only purely say physical separation. But then the question whether to discharge it, say mid-water column or deep sea. From environmental point of view, we know that in mid-water column, we cannot prove whether that is really harmful or not. But people have an expectation. And for discharging close to the seabed, there it's in that sense convenient because that area is already impacted. So you're at least impacting the area that is already being impacted anyhow. But from a technical point of view, then there's also the question, you can discharge it back to the seabed, but it's more complex. You need, instead of 1 kilometer or say 1.5 kilometer system, you need 5 or 6 kilometers. There's a lot of additional storage needed. There's more energy needed to drive the system. So there are quite some challenges there as well. Flow assurance becomes a bit more complex because you have a longer system. And it depends what regulations say what we need to do.
Thanks a lot. And maybe I can a follow-up question, asking the other way around, because you're the expert. What is it that you are perhaps most concerned of when you look at all of the activities happening? Which future would scare you?
I think the biggest risk that I see is being able to sufficiently contain the sediment plume, and in that sense, that we really know what are, say, the implications of that sediment plume in terms of what part of the area can be considered as mineable. Because if the plume is if we're able to restrict the plume quite close to the mining site, it also means that we can be more effective in creating, say, those corridors of areas that we leave untouched, and then we can do it in a more responsible way. But if that plumes will be generated in the wrong way, and then we create far wider disturbance than anticipated, then we're wasting a lot of resource, because that basically means that we need to keep a larger distance to the corridors that we decide that we should keep intact.
Thanks.
Thanks a lot.
I have one maybe final question, and that is, I think you also framed it at a certain moment like that it's a choice between that we have to make as a society, because we also want the energy transition to happen, and we need a lot of materials for that energy transition. So I fully agree with that. Yep. But at the same time, I also because that is my expertise. I know a bit about where to find these materials and how much would we need in the future, etc. So first of all, it's important to note that that the time frame in which we need these materials for the energy transition is, let's say, from now on till 2050 or 2060 or so. So this is a limited time frame.
Yes.
So in that time frame, we have to mine the materials that are required. Now, the scale up of deep sea mining is well, the first tests are being done. So before we have really large scale deep sea mining will take a while. I'm not sure how long you think it will take, but it might take a while, right?
It has a different scale up potential compared to conventional mining or land-based mining. So the metals company envisions, so that's the one that's envisions to start the earliest, and they have the ambition to start in 25 with a economic scale system.
Yeah.
And if we look at most of the other contractors, they expect to be fully economically operational by 2030.
But when do you think it will be 10% of the total world production of, if it would be scaled up as soon as we could do, how quickly do you think we can reach, let's say, 10% of world production of certain of these materials?
I never made those calculations, so I'm sorry there.
It would be interesting to do that, actually, because I think it's important, because if you frame it like we need this material for the energy transition, it should also be clear how much you can actually produce in the next couple of decades. And I'm also quite critical about this argument, because I think that in principle there's plenty of resources on from land-based sources. So we don't need, let's say, the deep sea resources. It might be cheaper, it might be more attractive commercially, or something like that, or it might be in the hands of other people. I mean, of other countries. That might all be true. But in terms of the amount that we need and the amount of materials that we need, we don't really need deep sea mining. So that is a that's why this frame is a bit problematic sometimes. So I think it's, I mean, if you could mine it without any environmental impact, then of course, yeah, why not?
Exactly, yes.
Yeah, and it's also fair to say, well, you should just compare the impacts to the impacts of land-based mining and then see which is more preferable. But that is problematic, because for land-based mining, you know exactly what you're talking about, because we have a lot of experience there. We know what kind of risks we are taking. While for ocean mining, we don't really know yet, and there's still a lot of research to be done, and it's very complex, as you also indicated. It's very difficult to do that kind of research.
One thing that's very important in this context. So at this point, exploitation is not possible. But all the efforts need to be done to assess whether exploitation is actually an option.
Yeah.
And that without getting data, we will never know.
Right.
So that's something that needs to be figured out. Yeah. As a scientist, I have say a bit more convenient position, so it's not my money on the line. But yeah, that's up for discussion. It's not yet been. It hasn't been decided. It all depends on what regulations will be. Whether there's we end up with something that has a viable business. If there's no viable business, then it will stop.
Yeah.
Very clearly.
Yeah.
And that's also for land-based mining. If there's no viable business, no mining contractor will do it.
Yeah. No, that's true. And one of the things that is connected to that is also that you can now see that certain OEMs already have said made statements that they don't want to have minerals coming from the deep sea, simply because they are kind of wary about it for the time being. At least they say no, we don't want that, because we don't know exactly what kind of consequences it might have, and we are all for responsible sourcing, and we don't think that this is yet, at least, under the heading of responsible sourcing.
Yeah, there the question also comes into play. So those are typically the major users.
Yeah.
So they are large enough that they can say, and that they can source sufficient from other sources. And I'm wondering how it will be for the smaller companies. Whether they have that luxury as well, and how they balance.
Yeah, and also companies that are maybe not in Western countries that
that's
on top of their list of priorities.
That's also a huge difference in perspective in terms of how Europe approaches it, and for instance how China approaches.
Yeah.
So
And,
that's also something to weigh in the discussion, and that makes it that complex, and it goes far beyond my own expertise. I'm more in the engineering sciences, so more about technology and say those kind of disturbances that will be generated. But that's also why I have this slide. It's all about getting all the disciplines together to really think up of what is the best way forward, and under what conditions might it be an option or not.
Yeah.
And to provide that advice to the governments, and then it becomes a political decision.
Yeah. And one other thing I think to note is that even if, let's say, the international community says we are not going to use international waters for seabed mining, that doesn't mean it won't happen, because there's all these territorial and economic zones around island states that can still be used for that if they decide that that's a good idea.
Also, we have to keep in mind, we also mine the seas for sand.
Yeah. Yeah.
And that's typically something we have accepted.
Yeah. So these are quite complex discussions indeed. Yeah. Yeah. But I'm I think we're about running out of time. I really thank you for sharing all your technical knowledge about this interesting topic, which will, I mean, this will remain on the agenda for quite a while. I think this is something that will proceed.
I expect so. Yes.
Yeah. And it's good to have all these different perspectives, but also from the technical side, it's really important to understand what is really going on. So I thank you a lot for joining us, Rudy, and explaining that to us. And I guess the discussion is something to be continued.
Yes, for sure. We're not there yet, and it's very good to have these kind of discussions.
Yeah, I think
in the end, it helps to give better advice to the people who are in charge.
Indeed, I fully agree. So thanks again. Thanks all for listening in, and I hope to see you next time during the next talk. Okay.
Thanks a lot. Bye-bye.